So now that we're done with Unit 1, we're going to finish up that last part of Chapter 5, the Sedimentary Archive. It was just kind of it seemed like a natural place to split the units because a lot of your labs are going to go along with some of the information you're going to learn today. So the first part of this next piece of Chapter 5 is about how we're going to use sedimentary rocks to solve geologic problems. So very often, geologists will name rock units. Rock units are bodies of rock that have a distinctive feature. They are not necessarily, a rock unit isn't necessarily all deposited at the same time, but it might have a really distinctive lithology. So a lithology is like a rock name, like it might be, or a rock type. So it might be a limestone or a black shale or a green shale, something distinctive about it. It might have a very definite stratigraphic position. So if we have these three rock layers, A, B, and C, are not rock layers, but outcrops, and they're composed of these rocks that are recorded at those sites. If you see a siltstone here, and that siltstone is underlain by a sandstone and overlain by a shale, and then we drive 30 miles to the east and we see another siltstone that is underlain by a sandstone and overlain by a shale, we might assume that those are the same rock layers. So that way we could be in Buffalo, New York and find a stack of rocks, and then drive to Batavia, New York and find a stack of rocks, and then have some idea about whether or not we're looking at the same rock or we're looking at a different rock. And another thing is that rock units are very often named. The first name typically has to do with the location where the rock is first described. So there is a rock layer in Rochester called the Kodak Sandstone. The first name refers to Kodak, the building which the sandstone was first described by near one of the Kodak buildings, and sandstone is the lithology. Similarly, there's a rock layer that has a lot of eurypterid fossils in New York that's called the Bertie Dolostone. And again, Bertie is the town where that rock layer was first described. Dolostone is the lithology. So it's also true that sometimes the geologic history of a couple rock layers might be connected. And so then geologists can group those rock units together to form groups, for lack of a better word. So here is this is a column of rocks that are found in the Grand Canyon, not all the way to the base of the Grand Canyon, but nevertheless in the Grand Canyon. And you can see that there's a rock layer called the Kaibab Formation, which is a limestone, and the Toraweep Formation, which is a shale. And then you can see that there is a rock group here called the Hermit Group. And the Hermit Group is composed of the Hermit Shale and the Coconino Formation, and then this symbol usually means that there's a lot of cross-bedding in the Coconino Formation. So this might be something like perhaps the Coconino Formation was formed in a stream, and so you have cross-beds, and the Hermit Shale is formed on the floodplain adjacent to the stream. So you could group those together because a floodplain and a river are naturally sort of connected. They just formed over different periods of time, and so they're connected into what's called the Hermit Group. Similarly, you can take a rock layer and you can split it into members, and that's what's happening down here in the Red Wall Formation. So if you look at the Red Wall Formation, it's been split into four members, right? The Whitmore Wash Formation, the Whitmore Wash member, Thunder Springs member, Mooney Falls member, and Horseshoe Mesa member. And you see that they're all limestones, but their patterns are differently sized here. So that is usually a clue that geologists use to indicate when limestone weathers, is it thinly bedded, like we might see it more in the Whitmore Wash limestone, or is it more thickly bedded like we see in the Thunder Springs member? And then this, based on a little bit more research, we might find out has to do perhaps a little bit with sea level, perhaps a little bit with wave action. We'd have to look a little bit closer, but nevertheless, they're the same rock type, so they might have a similar history, but they're very small rock layers that we might not be able to trace from place to place quite as easily because they might be relatively thin. So you might be able to find a member from Rochester to Batavia to Buffalo, but you might not, because again, they're smaller subsets of rock units. And to be honest, all of this has a certain amount of arbitrariness to it, because again, this is just how people organize rock layers based on their own interpretations. So we can look at rock layers and name them, but that doesn't necessarily mean that all of the rock layers, if we might find a shale in Buffalo, a shale in Batavia, and a shale in Rochester, that doesn't mean that they were deposited at the same time. We can find rock layers, we call rock layers that were deposited at the same time chronostratigraphic units. So chrono means time. So we're looking at layers of rock organized by time, because stratigraphic means the study of layered rock. So a chronostratigraphic unit is a rock layer that was deposited during a specific interval of time. So all of the sediment that we see in this diagram is a chronostratigraphic unit because it's all deposited currently, right? So we have sand that was deposited, then shale, and then limestone. Over time, though, sea level might change, and we can see here it looks like sea level rose a little bit. And when that happened, more sand got deposited, but it got deposited further upshore. So if we're just interested in rock units, in fact, I might just switch here real quick to a pen. If we were interested in rock units, we would say, look, here's the sandstone, right? And here's the shale. And there's the limestone. But we know that those weren't all deposited at the same time. A chronostratigraphic unit are these things here, timelines. All of these rocks below were deposited around the same time, and all of these rocks below were deposited at the same time, and so on and so forth. So you might say, how can you look at rock layers and figure out when they formed? Well, there's a couple clues. Fossils are a good one, especially if you have a fossil that only lived for a very short period of time and then went extinct. That's called an index fossil. That's super useful. Maybe you have a volcanic ash bed. Volcanic ash beds sometimes will be preserved very well in rock layers. Volcanic ash falls at all the same time, and they also have isotopes in them typically because they contain zircon crystals, and we can do some fun radioactive dating to figure out when that ashfall fell. So those are the sorts of things that we want to look for to be able to figure out. I always forget which one. I just want to go back to an arrow. Visible arrow. Okay. So when we go back, that's what we look for to figure out what is a chronostratigraphic unit. So I mentioned on the last slide that it looks like between those two diagrams that sea level rose. So that's a concept called a marine transgression. It's when the sea apparently rises and floods the land. And so the sea transgresses over the earth. And that can occur over a period of time. There's a couple reasons why it might seem like sea level rises. So today, in our time of climate change, sea level rises because of climate change, because the climate is warming, right? And so a lot of mass of ice shelves and ice sheets are melting and flowing into the ocean. And then water, when it heats up, tends to expand, and all of those things result in sea level rising. So that would result in a marine transgression. That's an example of something that's local. And the word that geologists use, that's something that's global. The word that geologists use for when a phenomenon is global is eustatic. So eustatic means global. So a transgression can occur because of global sea level rise, or it can occur because of something local, like subsidence. So a lot of times in earthquakes, there are motion along two sides of a fault, right? And so when that happens, one side of the fault that drops down, when that occurs, that piece of land moves down in elevation. And so locally, if you're suddenly dropping in elevation, it looks to you like sea level is rising. It's not, you're just kind of sinking a little bit. So to figure out if a marine transgression is local or eustatic, you have to do a little bit more digging. So you have to find a marine transgression in one location and then maybe find evidence for it on a completely other side of the globe. And you can check that. That's the part of the strength of the scientific community is that you can figure out what the rock record looks like in other places by working with your colleagues. So what this means is that this sandstone, shale, and limestone during a transgression is going to move further and further on land as sea level is rising. We're going to define the word facies in just a second. So this is a repeat of the diagram you saw on the last slide, where here you have time 1, and then here you have time 2. So the shoreline used to be here, right? And so you had sandstone, shale, limestone. That's, as we said earlier, a really common sequence of sediment that we see as we move offshore. And so as sea level rises, that same pattern is replicated of sandstone, shale, and limestone in time 2. Sea level continues to rise here in time 3. And then we have this third horizon of time 3 of sandstone, shale, and limestone. So what I want to point out to you is that we have this same sequence here of, as we go from bottom to top, of sandstone, shale, and then limestone. That is really, and this is the abbreviation for sandstone, shale, and limestone, that is a really easy way to identify a marine transgression. And so if you ever get confused, the reason is because sandstone is right at the seashore, right? And then shale is quiet water and limestone is deep water. So in one location, we went from the beach to offshore to deep water. So that is a marine transgression. The opposite is called a marine regression. So that is a period of time when it appears that sea level is falling. And so instead of sea level advancing over the land, sea level is retreating from the land. And I want to warn you that this diagram is not fantastic. But here we see that same sequence of sandstone, shale, limestone, and we know sea level is going to fall. And sea level may fall for the opposite of the reasons that sea level rises. So instead of sea level rising because of global warming, global cooling will cause sea level to fall globally because water will be taken out of the ocean and stored on land in the form of ice. So sea level will fall, or alternatively, the local land could be uplifted. And so then it would look locally like sea level were falling, but it's not, it's just falling. You're just at a higher elevation. So let's look at what that would look like in time sequence. So here we have time 1. And then we know our facies of sandstone, shale, and limestone are going to migrate further offshore as sea level migrates offshore. Here we have time level 2, and we're starting to we see sea level is falling. So the sand is only being deposited here now. And for time level 3, sea level has fallen even further away. So what you start to have is the opposite of what you saw during a marine transgression. You have limestone, shale, and sandstone from bottom to top. And so that's what is illustrated here. Limestone, sandstone, shale from bottom to top tells you it's a regression because limestone is deep water, shale is offshore, and sandstone is the beach. So this is telling you in one location, based on superposition, you went from deep water to very shallow water. Cool. So this idea that we can find a sequence vertically of sandstone, shale, limestone, shale, sandstone. I'm tripping over my own mouth a little bit today. Is a sequence that we can see vertically, but it's also a sequence that we see horizontally, which is kind of fun. That is a law that we're going to learn about on this slide. And I also use the word facies, so let's define that. So facies are all the characteristics from which a depositional environment can be inferred. So sandstone is important, right? Because we've been interpreting it as it's only the beach, but sandstone can be formed other places too. But when we are at the beach and the sand is white and it's well rounded and it's well sorted and maybe there's some broken up shell fossils, those are all parts of the model that tell us, hey, when we have all of these things, we're looking at a beach environment. So we can tell that by lithology, sandstone here. We can look at fossil assemblages. What fossils are we seeing? And that idea that the lateral succession of facies side to side can also be seen vertically is called Walther's law. So here's a diagram that's a little bit better to illustrate the phenomena that we were just talking about. So here we have a situation where sandstone has clearly been climbing closer and closer onshore. So this is a marine transgression, and we can see that when we look right here at column B, right? Because we have sandstone, siltstone, shale, and limestone. So this is the beach to offshore to deep water. So that's a transgression. And we can see that same phenomenon when we go laterally. So sandstone to siltstone to shale to limestone. That's called Walther's law, and you can use it in a basin so that if you were looking for one specific rock layer, like maybe there was a mineral in this clay that you were looking for, you could use that to figure out, all right, based on the slope of these rock layers and based on the sequence, where you would go to, or whether you would expect to find it higher or lower in an adjacent sequence, because you know a little bit. So when you're standing at one location, you can use that to kind of figure out what's going on across the basin.